All right, Michael, you got the answer?
I'm still carrying some squareds.
You want to talk it through?
Okay, sure. So x is really x1, x2, and y is really y1, y2. And phi x is now this crazy triple x. So I wrote down x1 squared, x2 squared, square root of 2, x1, x2.
Yep.
That's the vector that we get for phi x. And then for phi y, I get y1. It seems like it would be helpful to see this.
No, do you want me to write it down?
Sure.
Okay. So that turns out to be the same as, what do you say? X1 squared,
Uh-huh. x2 squared,
x2 squared,
root 2, x1,
and
x2.
root 2, x1, x2. Okay.
And then the y vector gets transformed to the same thing except for with y's. Y1 squared, comma, y2 squared, comma, root 2, y1, y2.
Okay.
So then the dot product is just the products of the corresponding components summed up. So x1 squared, y1 squared, plus
Okay.
x2 squared, y2 squared,
Mm-hmm.
2 x1, x2, y1, y2.
That's right. So here's a question for you, Michael. Does that look familiar based on your years of thinking about algebra?
Oh, thanks for writing it that way. I see. Is this right? So it's like we can factor this. It's
Mm-hmm.
like x1 plus x2 times y1 plus y2.
Yeah, that's right. Wait, is that right?
No, it's not right. x1 y1
Mm-hmm.
plus x2 y2, whole thing squared.
Right. So let's write that down. So if you factor it out, you're right. This is exactly equal to x1, y1 plus x2, y2 squared. And what's an even simpler way of writing that?
I see. x1 y1 plus x2 y2 looks like a dot product itself. It looks like the dot
Mm-hmm.
product of x and y. Oh, it's x transpose y on the inside, and then we square it on the outside.
That's exactly right. So now do you see why there was method to my madness when I created the phi function?
Not yet. So you're saying if we're just dealing with dot products, no, I'm still a little confused. So it is the case that you define these in an interesting way so that the dot product became the square of the old dot product.
Right. So now let me make two observations. Okay? Here's observation one. What's x transpose y? I mean, geometrically, what does that represent?
The length of the projection of y onto x.
No, I mean geometrically. Like, go all the way back to geometry. Third grade.
We didn't do transposes in third grade.
I know we didn't do transposes, but you did equations like this, or at least later you learned they were equations like this. Here, pretend you're in third grade, and I said, talk to me about geometry. What kind of words would you use?
Oh, what's in geometry? Triangles, circles.
Yeah. Circles. Did you say circles?
Sure, but only because I thought you might wanted me to.
Did you say circles?
That's really ugly looking circle, sure.
Sure. This is basically a particular form of an equation for a circle, which means that we've gone from thinking about the linear relationship between xi and xj, or your data points, and we've now turned it into something that looks a lot more like a circle.
Interesting.
So, if, and this is my second point, Michael, if you believed me in the beginning where we noticed that xi transpose xj is really about similarity, it's really about why it is you would say 2 points are close to one another or far apart from one another. By coming into this transformation over here, where we basically represented the equation for a circle, we have now replaced our notion of similarity from being this very simple projection to being the notion of similarity is whether you fall in or out of a circle.
So more sort of about the distance as opposed to what direction you're pointing.
Right. And both of them are fine because both of them represent some notion of similarity, some notion of distance in some space. In the original case, we're talking about 2 points that are lined up together, and over here with the circle, with this particular equation, we've represented whether they're inside the radius of a circle or outside the radius of a circle. Now, this particular example assumes that the circle is centered at the origin and so on and so forth. But the idea I want you to see is that we could transform all of our data so that we separated points from within one circle to points that are outside of the circle. And then if we do that, projecting from 2 dimensions here into 3 dimensions, we've basically taken all of the pluses and moved them up and all of the minuses and moved them back. And now we can separate them with a hyperplane.
Without knowing which ones are the pluses and which ones are the minuses, of course.
Of course.
Because, I see, because they're the ones that were closer to the origin.
Right.
So they get raised up less. Wow. Okay. So you're using that third dimension.
Right. Now, this is a cute trick, right? I can basically take my data and I transform it into a higher dimensional space where suddenly I'm now able to separate it linearly. That's very cute. But I chose this particular form for a reason. Can you guess why?
Because it fits the circle pattern that you wanted.
But there are lots of different ways we could have fit the circle pattern. I chose this particular form because not only does it fit the circle pattern, but it doesn't require that I do this particular transformation. Rather than taking all of my data points and projecting them up into 3 dimensions directly, I can instead still simply compute the dot product. And now I take that answer and I square it.
So you're saying in this formulation of the quadratic program that you have there in terms of capital W, if you write code to do that, each time in the code you want to compute that xi transpose times xj, if you just squared it right before you actually used it, it would be as if you projected it into this third dimension and found a plane?
Yes, that's exactly right.
That's crazy.
It's so crazy it has a name, and that is the kernel trick. So again, if we really push on this notion of similarity, what we're really saying is we care about maximizing some function that depends highly upon how different data points are alike or how they are different. And simply by writing it this particular way, all we're saying is, you know what, we think that the inner product is how we should define similarity. But instead, we could use a different function altogether, phi, or more nicely represented as x transpose y squared, and say that's our notion of similarity, and we can substitute it accordingly.
So we never really used phi.
We never used phi. We were able to avoid all of that by coming up with a clever representation of similarity that just so happened to represent something or could represent something in a higher dimensional space.
But so is it important that such a phi exist, or is it just the case that we can, you know, if we could throw in a cubed, we could throw in a fourth, we could do a square root and a log. Like, can we do anything we want there in that xi transpose xj, or are we constrained to only use things that somewhere out there's a way of representing it as a regular dot product?
Well, that's an interesting question. The answer is you can't just use anything, but in practice it turns out you can use almost anything. And the other answer to your question is, well, it turns out for any function that you use, there is some transformation into some dimensional space, higher dimensional space, that is equivalent.
Whoa.
Now, it may turn out that you need an infinite number of dimensions to represent it, but there is some way of transforming your points into a higher dimensional space that happens to represent this kernel, or whatever kernel you choose to use.
So which part is the kernel?
So the kernel is the function itself. So in fact, let me clean up this screen a little bit and see if we can make this a little bit more precise and easier to understand.